Ground improvement methods are used to enhance the engineering properties of weak or problematic soils so that they can safely support structures, embankments, roads, and infrastructure. These methods aim to increase bearing capacity, reduce settlement, improve stability, and control groundwater or deformation. The choice of method depends on soil type, depth of weak layers, project scale, time constraints, and cost. Soil replacement is one of the most straightforward ground improvement techniques. It involves excavating weak or compressible soil and replacing it with stronger, well-compacted granular materials such as sand, gravel, or crushed stone. By physically removing the problematic soil, the foundation rests on a more competent layer, leading to immediate improvement in bearing capacity and reduced settlement. This method is most effective where weak soils are shallow. However, it becomes impractical and costly for deep deposits due to excavation depth, dewatering needs, and disposal of unsuitable material. Compaction improves soil by densifying it through mechanical energy, reducing voids and increasing strength and stiffness. This is commonly achieved using rollers, rammers, or vibrator equipment at the ground surface. For deeper improvement, dynamic compaction, where heavy weights are repeatedly dropped from height, may be used. Compaction is highly effective for granular soils such as sands and fills, but it has limited benefit in soft clays where excess pore water pressure prevents effective densification. Preloading, also known as surcharge loading, improves weak soils by applying a temporary load greater than the expected permanent load before construction. This load induces consolidation in compressible soils, particularly soft clays and silts, forcing water out of the pores and reducing long-term settlement. Once the desired settlement has occurred, the surcharge is removed and the permanent structure is built. While conceptually simple and reliable, preloading requires time and sufficient space, and stability during loading must be carefully checked. Vertical drains are often used in combination with preloading to accelerate consolidation. They consist of prefabricated vertical drains, PVDs, or sand drains installed into soft clay layers. These drains shorten the drainage path for pore water, significantly reducing the time required for consolidation. Vertical drains do not strengthen the soil directly, instead, they enable faster settlement under applied loads. They are particularly effective for large-scale projects such as embankments, roads, and airport platforms constructed over thick soft clay deposits. Stone columns are formed by replacing or displacing soft soil with compacted gravel or crushed stone columns. These columns act as reinforcement within the soil mass, increasing bearing capacity, reducing settlement, and improving drainage. They also help mitigate liquefaction in seismic areas. Stone columns are suitable for soft clays and silts but may be less effective in extremely soft or organic soils where lateral confinement is insufficient. Lime and cement stabilization improves soil by chemical modification. Lime is typically used for clay soils to reduce plasticity, shrink swell behavior, and moisture sensitivity, while cement increases strength and stiffness through cementation. The stabilizing agent is mixed with the soil in situ or in a plant, creating a stronger and more workable material. This method is widely used for road subgrades, working platforms, and lightly loaded structures. Its effectiveness depends on soil mineralogy and proper quality control during mixing. Grouting involves injecting fluid materials such as cement grout, chemical solutions, or microfine cement into the ground to fill voids, bind soil particles, or reduce permeability. It is often used for localized ground improvement, underpinning existing foundations, or seepage control. Grouting is highly adaptable and precise but can be expensive and requires specialized expertise. Its success depends heavily on ground conditions and proper control of injection pressures and volumes. Deep soil mixing, DSM, improves weak ground by mechanically mixing in situ soil with binders such as cement or lime using specialized equipment. This process creates soil cement columns or panels with significantly higher strength and stiffness. DSM is particularly suitable for very soft clays and organic soils where other methods may be ineffective. It provides substantial improvement with minimal excavation but is relatively costly and requires strict quality assurance. Vibrocompaction is a technique used to densify loose granular soils using a vibrating probe inserted into the ground. The vibration rearranges soil particles into a denser configuration, increasing strength and reducing settlement and liquefaction potential. It is most effective in clean sands and gravels and generally requires the presence of groundwater. Vibrocompaction is not suitable for cohesive soils such as clays. In practice, ground improvement is rarely a one-size-fits-all solution. Engineers often combine methods, such as surcharge with vertical drains or geosynthetics with soil replacement, to achieve optimal performance. A thorough geotechnical investigation is essential to select the most appropriate technique, balancing technical effectiveness, construction time, environmental impact, and cost.